In this lesson, we're going to introduce exponential functions. And so our main goals today are to be able to recognize the equations of exponential functions and also be able to sketch graphs of exponential functions and apply the ideas of transformations that we already know to this new type of function. So to begin here, we're going to look at kind of an interesting situation. It says, how many times must we fold a piece of paper so that it could reach all the way to the moon? Now the moon is about 15.1 billion inches from Earth, and we're going to assume that our piece of paper is about 0.03 of an inch thick. So this is exactly what it sounds like. You have a flat piece of paper sitting on the ground. If you folded it and folded it again and folded it again, how many folds would it take so that the new thickness of that piece of paper would get us to the moon, essentially? So let's start with if we hadn't folded it at all, we would of course just have the thickness of the piece of paper, right? So be 0.003 of an inch thick. If I folded it once, of course, it would double, right? It would double in thickness. If I folded it again, so 2 folds, then it would double in thickness again, right? Okay. And if I did it again, it would, of course, double again. So we're just kind of trying to observe the pattern that's happening here. All right, and so we see what's going on. Now, I put another column here so we can express some of these ideas a little differently. So one way to think of this is that here I took my original 0.003 and I just times it by 1. Here I took the original 0.003 and I times it by 2, and then by 4, and then by 8. And of course that gives me the same numbers that I had in this first column. And then lastly, what I'm going to do is I'm going to express these as a number raised to a power. Now 1, 2, 4, and 8 are all powers of 2. The 1 is a power of 2 in the sense that it is 2 to the 0 power, because anything to the 0 power is going to give you 1. Of course, this is going to be 2 to the first power. 4 is 2 to the second power. And 8 is 2 to the third power, right? Because 2 times 2 times 2 is 8. So what we've got now is this nice pattern going, and so at this very last row it says, what if I do n folds, right? I haven't specified the number of folds. Can I come up with an expression for that? If I just follow the pattern, the exponent always corresponded to the number of folds, so that must mean that my formula is 0.003 times 2 to the n. And so to answer this question that they've asked, which is how many times must I fold a piece of paper in order to reach to the moon, all I have to do is set up this equation, 15.1 billion, so that would be 10 to the 9th power. When does that equal 0.003 times 2 to the n? And so we will talk later about how it is you go about solving an equation like this, but the interesting thing is that this is about 41. So the exponent only has to be about 41 in order to really actually get you past this number. So what that means is that all I would have to do is fold a piece of paper 41 times, and its thickness would be greater than the distance from the Earth to the moon. Now this might seem surprising, but it shows us the power of what we call exponential growth and how fast it can take off once it gets going. But the catch here is that you can't fold a piece of paper that many times. I think you can only fold a piece of paper about 7 times maybe. So you could take out a piece of paper and try that, and you're not going to have very much success after about 6 or 7 tries. In fact, there's a Mythbusters episode, an old Mythbusters episode, where they actually put this to a test with a giant piece of paper, and I think they might get 8 or 9 times out of it, but I think a steamroller's involved, and so while this might seem like a surprising result, it's also not that practical of a result. All right, so here's our general form for an exponential function. And so if you look back here, we had this number that never changed throughout, 0.003, and then we had this number that got raised to a power 2. And so what we'll tend to do is call this number A, and then the number that's being raised to a power B, and B stands for base. So we express our exponential functions like this. So A times b to the x power. So on our previous page, A was 0.003, B was 2. Or a lot of times what we'll also do is express it as 1 times 1 plus r to the x, where we can say that r is the growth rate or the decay rate, depending upon whether it's positive or negative. All right, but these will be the general ways that we'll see our exponential functions written. A will refer to as the initial or the starting point, right? Remember in the last slide, we started with just a piece of paper. So we started with the thickness of a piece of paper. And so in other words, when our exponent was 0, that was the number our function was equal to. And then we call B the growth or decay factor. Okay, so R is the percentage growth or decay rate, and B is the growth or decay factor, what we're actually multiplying by over and over. And just a little note here, we're only going to do positive values for B. All right, so here's kind of a busy slide that's got kind of 2 pages of your notes all in one. So what we've done over here is graph 2 exponential functions. On the one hand, 3 times 2 to the x, and 3 times 1/2 to the x. And so 3 is our a value. It does not have an exponential that it's being raised to. It's the 2 and the 1/2 that are the bases of the exponent. And you can see how this behaves. So in this case here, when you plug in negative numbers for the exponent, from our exponent rules, remember that if you have x to the negative n, that equals 1 over x to the n. So this 2 to the negative 3 becomes 1 over 2 to the 3rd. So that would be 3 over 8 ultimately. Right, same thing here. 2 to the negative 2 is 1 over 2 squared, so they get 3/4. And then of course the positives just give us positive answers here. And so what happens here is in this this function, we have exponential growth. As the x value gets larger, the y values get bigger and kind of explode out of control. And then just the opposite happens with this function g of x. So we're starting off with a base value that's smaller than 1. So what that does is when we're raising to negative numbers, that flips it essentially, or it sends the 2 to the negative 3 up to the top. And so we get our larger numbers when the exponent's negative, and then our smaller fractions when the exponent is positive. And so we call this exponential decay. Right? So as the x values get bigger, the y values get smaller. Okay. So some observations from all this. First of all, a, when your function looks like a times b to the x, is always the vertical intercept of the graph. Okay? Or in other words, 0a is always a point on the graph. B, the base, determines the rate at which the graph grows or decays. Okay? So b is the base, and it's going to be an increasing function or an exponential growth function when b is greater than 1, as you saw up here. When b was 2, we had exponential growth. And then when b is between 0 and 1, that's when we get exponential decay, just like in g of x. Another thing to notice is that when you look at these two equations, there is no way that you could make a negative number out of them. So what's happening, let's look at g of x. Even though it's approaching y equals 0 as we go, it will never dip down below that x-axis. So it's approaching it. And so just like we had with rational functions, we're also going to have horizontal asymptotes with exponentials. And so when your function is f of x equals a times b to the x, your horizontal asymptote is just y equals 0. We can also talk about concavity. The graph will be concave up if a is greater than 0 and concave down if a is less than 0. So that initial value, whether it's positive or negative, that'll tell you about concavity. And then number 5, the domain of the function is all real numbers. You can see there's no x values I can't plug into the function, right? And looking at the equation, there's no roots that I need to watch out for, and there's no way I could divide by 0. And then the range is 0 to infinity. Just like we said, there's no way I can get a negative out of that equation. All right, so with those basics, let's work on actually sketching a graph. So 2 points that are always nice to keep in mind that are always going to be on your graph are, we mentioned this on the previous page, 0a, and the one we didn't mention was the point 1, comma, ab, right? And that is because, right, if our function looks like this, then if you plug in 0 for x, you're going to get a b to the 0, but we know b to the 0 is just 1. So f of 0 equals a. If I say f of 1, then that's going to be a times b to the 1, which is just ab. And so that's where those 2 points are coming from. So a good way to get this graph going here would be just to say that I know that I can graph the point 0, 6, and I can graph the point 1 6 times a third, but that's just the point 1, 2. So I'll go ahead and put in 0, 6, 5, 6, and then 1, 2. And I'll remember from what we learned on the previous page that when this b is between 0 and 1, that's when we get exponential decay. And I should be approaching y equals 0. So here's the picture of what we got going on here. Approaching the x-axis but never actually touching it. And so this would be my exponential decay function that I see in example 1. All right, so the other thing we are going to do is we're going to apply the ideas of transformations of functions to exponentials. So what we should start by doing is when we see a function like this, let's understand that when we put this plus 3 here, if we think of g of x as a transformation, negative 2 to the x plus 3, then let's think of it as a transformation, of the more basic looking exponential, y equals negative 1 times 2 to the x. Okay, so where a is negative 1 and b is 2. Then if I think of this as the base function, then it's clear that that plus 3 is a vertical shift because I'm adding it to the y values. So let's start by just graphing this and then seeing how the vertical shift affects things. All right, so like on the previous page, we know that 0, -1 is a point on this function, and we know that 1, -1 times 2, so 1, -2, is also a point on this function. So let's graph our base function here, 0, -1, and 1, -2. I know that y equals 0 is a horizontal asymptote, and so this must do something like that, and then over on this side approach the horizontal asymptote of y equals 0. Okay, so there's our base function there. All right, so what we can see then is that this here, let's circle that in red, is just this function but shifted vertically up 3. So what's that going to do? Well, that's going to move my horizontal asymptote up. And anytime our horizontal asymptote is not lying on the x-axis, we should actually draw it in. So I'm going to shift everything up 3. So that would be this point, 1, 2, 3. This point, 1, 2, 3. And then also my horizontal asymptote. So I'll make sure I make it clear where my graph is approaching in the negative direction there. All right, and it never hurts just to plug in other points too. Like I'm going to put a little point right here. I can see that if I plug in x equals 2, I'm going to get -4 plus 3. So -4 plus 3 is, of course, -1. And so, oops, I put that in the wrong spot. So I'm going to have a point right here. And so that'll allow me to be a little more accurate here. And then we'll approach the horizontal asymptote on the left. All right, so let's do another one here. So what are we going to think of as our base function? Well, let's just think of plain old y equals 3 to the x. And of course, let's remember that when we have y equals 3 to the x, the a is really the number 1. So a equals 1 and b equals 3. So that means that we have the point 0, 1, and we have the point 1, 1 times 3. So 1, 3. So we can put those both in there. And we know that that 3 is bigger than 1, so this is going to be exponential growth. So doing something like that. And then approaching our horizontal asymptote over here on this side. All right, so there's our base function. All right, so what has h done to this base function? Okay, well, it looks like when I think about, I'll rewrite it down here so I have a little more room. I have some subtraction going on with the x, and then I have some subtraction going on out here. So like in the last example, we realized this was a vertical shift. A vertical shift down 2. And then here, because it's happening to the x, it's also a shift, but it's a horizontal shift. And just like before, if we have a horizontal shift, it's always kind of the opposite direction that you might expect. So it's a horizontal shift because it's -1 to the right by 2, or excuse me, to the right by 1. So each of these points are going to go over 1, down 2. Over 1, down 2. But we also saw how the vertical shift tells us that we have now a different horizontal asymptote, so our horizontal asymptote is now down as well at y equals -2. So we make sure that we put that in. Oh, sorry that I missed that. Okay. And so there's our transformed function of y equals 3 to the x, h of x equals 3 to the x minus 1 minus 2. All right, so now let's take a look at when we want to have or we want to come up with the equation for our exponential function in the form y equals a times b to the x, given some points we know it goes through. Okay, so if we recall that anytime the x is 0, that's going to be your a, the y value that it comes with is going to be your a, then that makes this pretty easy. So this one here is telling me that my equation is going to be y equals 3 times b to the x. And then from there, we got to use this information to figure out what b is. But this is just saying when x equals 2, we know that y is 75. So if I plug a 75 in for y and a 2 in for x, then this becomes a little equation we can solve. So we can divide by 3 on both sides. Excuse me, let me fix that real quick. So we'll divide by 3 on both sides. And that's going to give me that 25 is equal to b squared. And remember, b is always positive. So while we normally, when we take the square root of both sides, have to think, okay, is it plus or minus? In this context, it's always going to be positive. So b is 5. And so that means that our equation is y is equal to 3 times 5 to the x. Now in example 5, this is a little harder because they don't give us that initial value where x is equal to 0, where we could just say, oh, that number is a. Here they don't give us x equals 0. So that's a little trickier. So what we're going to want to do is set up a couple of equations where we plug in these values for x and y. So on the one hand, we'll be able to say that 2/5 is equal to a times b to the -1. And on the other hand, we'll be able to say 10 equals a times b to the 1. So in cases like this, one thing we can notice is that if we were to divide these equations, then the a's could cancel out, and that would allow us to figure out what b is. So the way this looks is we'll say 10 divided by 2/5 is equal to, well, since 10 is equal to a times b to the 1, we'll put that on top, and then 2/5 is equal to a times b to the -1, we'll put that on bottom. And so we can cancel out the a's, and so now we do only have one unknown that we're trying to find. So on the left-hand side there, we've got to simplify this. So this will be, let's go over here to get some more room. 10 divided by 2/5 is equal to, and then let's remember what we do. When we have like bases that we're dividing, we can combine them by taking the top minus the bottom exponent. So b raised to the 1 minus -1. On the left, we flip the second fraction and multiply. On the right, we get b squared. So here we get, when we simplify that, that would be 25 equals b squared. And so actually it's the same base as our previous problem. B must be 5. So what we can do is we can update what we know, right? I still don't know a, but now I at least know that b is 5. But at this point, now we can find a, because now we can plug one of these points back in. It doesn't matter which. I think I'll pick this one since there's no fractions involved. And then we can plug in 10 for y and 1 for x, and then solve for a. So we get that a must be 2. So now our final answer is y equals 2 times 5 to the x. All right, our last example here is basically doing a similar problem to those last two, but the information is given to us graphically. So what we want to do here is we want to find 2 points that are on the graph that are really clear what they are. So here's one. I think it's pretty clear that the point 2, 2 is on the graph. And then right here, it looks like the arrow is going right through 3, negative 4. Okay. So 3, negative 4. So now it just becomes a problem just like our previous one, really, except for one other thing, and that is I can see that there is a horizontal asymptote here. Okay? Even though they haven't drawn it in, and I suppose that perhaps they should have, but you will see them drawn without the horizontal asymptote showing. But it's clear that this exponential is approaching y equals 4. So we can also make note of that. Y equals 4 is a horizontal asymptote. And if you think back to our previous problems, we noted that our horizontal asymptote came from the fact of having a vertical shift. So if I have a horizontal asymptote of 4, then that must mean that the equation that I'm looking for isn't just y equals a times b to the x like the last 2 questions gave us. It's a times b to the x plus 4. All right, so from there, we can go ahead and set up similar situations to what we had in the last one. So on the one hand, if I plug in 2 for y, then that goes with an x value of 2. So just taking that from this ordered pair. Then taking that ordered pair, I get putting negative 4 in for y gives me a times b to the 3rd plus 4. So again, 2 different equations here. And in the last one we divided these, but before we divide them, we should definitely get the a times b to the power all by itself. So on the left I have negative 2 is equal to a times b squared. And on the right here I have negative 8 is equal to a times b to the 3rd. And now I can divide these. So I'm going to take the one on the right divided by the one on the left, so that I have a times b to the 3rd over ab squared. And I put this one on top so that in the end I would get just b to the 1st power after doing my simplification. That's going to be a whole lot easier. So I cancel out my a's. So we get 4 is equal to b to the 3 minus 2, but that just means 4 is my b. So to update this, we've got y equals, still don't know what a is, right? So y equals a, but then I do know that b is 4, and my horizontal asymptote is 4. But then lastly, I can just plug in an x and y again. So let's plug in 2 for y and 2 for x and solve. And then we'll be able to figure out our a. Sorry, I'm kind of running out of room here, so not the best use of space, but we'll make it through here. Negative 2 is equal to a times 16, and then I can divide by 16. So negative 1/8 is my a. So putting all this together, our equation is y equals negative 1/8 times 4 to the x plus 4.